Now, since the recent discovery that iron selenide superconducts at a relatively high temperature of 80 Kelvin, the whole world has really become vastly interested in this material. And as a result, everyone's been trying to figure out how do we make this crystal most effectively to maximize the superconducting properties. Now, few people have actually, however, gone and looked at the fundamental reactions between iron and selenium that lead to these structures. The problem is that crystal growth and formation is dependent on a variety of factors, two of which are thermodynamics and kinetics. Thermodynamics is a measure of how stable a material is, while kinetics is a measure of how easy it is for the atoms to arrange into a given solid state structure, in this case. We can think of it like rolling a ball down a hill. And in this case, I've provided the hill in this energy reaction coordinate diagram. Now, how deep this hill is a thermodynamic matter. However, how many little bumps along the way there are before you get to the bottom of the hill, now that's a kinetics problem. Now, what I'm interested in is seeing if I can get my ball stuck in a little bump along the way. The point at which this ball gets stuck, I'll say, is what we call a kinetically metastable phase. Saying it's not the thermodynamic product, it's semi-stable, but it's not the most stable phase you can make. In order to trap a kinetically metastable phase, you need the initial arrangement of atoms to look a lot like the final product you're targeting. This is analogous to making a cake by assembling it in layers, as opposed to just mixing all of the ingredients together in a bowl. If you want those layers, it helps to create them yourself, and then you bake the cake and you'll get your layered cake that you're after. Now, you can create these layers of atoms using a technique called physical vapor deposition. This involves heating up elements in their solid form, and in this case, iron and selenium, until the atoms fly off as vapors that eventually stick to some substrate, right up here. Similar to how a cake must be baked before it becomes a final product, these iron selenide precursors, is what we'll call them, can be gently heated to allow the crystals to form. Now, I can tune how much of a role thermodynamics is going to play in the formation of my products by changing the temperature that I'm actually going to heat these samples at, these precursors at. In the reaction coordinate diagram to the left, this is similar to giving the samples more energy to get up and over these little bumps so that they eventually reach the thermodynamic product. After heating, we can look at the structure of these samples using two techniques called X-ray diffraction and X-ray fluorescence. Now, I'll save you this long scientific explanation of these phenomena, except to say that certain crystal structures have characteristic X-ray diffraction patterns. And that's what we see here in the results. Now, I looked at two types of samples in my studies, samples with about 1 selenium atom for every iron atom, and samples with about 2 selenium atoms with every iron atom. I found that in both cases, the samples that formed appear to be heavily controlled by thermodynamics. This suggests that there are actually relatively few bumps along this energy reaction coordinate pathway. Rather, it's more of a smooth descent. Now we can kind of see that in these illustrations down below, where I have done all the calculations from the diffraction patterns, and I've actually generated the structures that iron and selenium atoms are arranging as a function of temperature. Now there are a bunch of quite a few different structures that form for each type of system, but these are all actually very well predicted by thermodynamics, with the exception of this sample. This again suggests a large degree of thermodynamic control in the iron selenide system. And all this is to say that forming any kinetically metastable iron selenide structures is likely not possible due to the low kinetic barriers and heavy thermodynamic control of iron selenides.